Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to look at organic compounds in general, what it means to be organic. But we're going to first start with what is inorganic as well. So, carbon-containing compounds that came from nature, that was our original definition of an organic compound. So it's something that wasn't able to be produced in the lab. Plants, animals, humans, we are made of a lot of carbon. We are organic. That was, organic compounds. However, in the early 20th century, we started to be able to produce organic compounds from non-organic material, and so definitions have changed since then. And so for the purpose of our course, we kind of talk about organic compounds being carbon-containing compounds with a few exceptions. So I want to talk about these few exceptions. So these here are not organic compounds, but they do contain carbon. So starting on the left here, carbonates such as carbonate or even hydrogen carbonate, these contain carbon in them, but they are not organic. They are inorganic. So this is actually an ion, and so it would be part of ionic compounds. So for instance, everybody knows baking soda, sodium hydrogen carbonate or sodium bicarbonate, or you could have things like potassium carbonate, or limestone like calcium carbonate. Okay, so all of these are ionic compounds. If you contain ions, you are definitely not an organic compound. Then we have cyanides, which are also ionic. So things like potassium cyanide, or you can even have thiocyanate, SCN minus. This also contains carbon. So again, something like sodium thiocyanate. Okay. Carbides are when carbon can act as an ion, which isn't all that common. Most periodic tables don't even list carbon having an ion charge, such as the one that we use. But carbides are actually a really important compound. Generally, they are used in a lot of things like cutting blades, drill bits, and things of that nature. But they also are used in jewelry. My wedding ring is a carbide, a tungsten carbide. So tungsten is W4+, carbide is C4-. So tungsten carbide. And you'll notice a lot of men wearing now black. They look almost black or very dark rings. And the majority of the time, those are tungsten carbide rings. They're ultra strong. They will not bend. You can't get them resized. And again, they're using a lot of heavy industry stuff, cutting blades and drill bits, etc. But generally what you're looking for with a carbide is you have a metal first, a metal ion, so iron, tungsten, something like that, and then it's followed by carbon. And then of course the ratios change, but tungsten carbide is a 4:4 ratio, and so it's a 1:1 ratio of tungsten to carbide. And then, of course, any kind of oxides of carbon, so carbon monoxide gas or carbon dioxide gas. These would also be considered not organic, but they do contain carbon. So for our memory, we really need to have these things down. Carbonates or hydrogen carbonates, cyanides, thiocyanate, carbides, and oxides of carbon are not organic compounds, and they do not fall underneath organic in any way. Okay, the next thing we're going to look at is a general overview of organic compounds and how we can kind of organize them in such a way that we can categorize them and kind of deal with each section one at a time. So the first thing I want to talk about is, organic compounds must contain carbon. That is the essential thing. And obviously it can't be one of the things that we consider non-organic that contain carbon that we just talked about. But the first splitting between kind of how you could divide them, the two major groups, would definitely be hydrocarbons. Hydrocarbons are carbon and hydrogen containing compounds only. So there would be no nitrogen or phosphorus or oxygen or halogens. The other grouping would be a hydrocarbon derivative. Now, a hydrocarbon derivative has to have carbon. It usually has hydrogen, but it doesn't have to. But then it would have to have something different, such as, I would say the most common things that it would have beyond carbon or hydrogen would be oxygen, nitrogen. Those would probably be the two most common other elements in an organic species. You may get some phosphorus. And then you can get some halogens as well. Now, the only ones that we're really dealing with, so halogens being things like chlorine, fluorine, bromine, iodine, okay? The ones for our course that we're dealing with are really just oxygens as well as halogens. But I don't want to take away from the importance of how big nitrogen is part of organic compounds. So the first thing we're going to look at, though, is we're going to focus on hydrocarbons themselves. So again, as I move up here, we kind of break down hydrocarbons into two major categories. And I do have to add a little bit to this for sure. But I'm going to break off to the right here first and talk about aromatics. Okay, so the first division is what we would call aliphatics and aromatics. Aromatics must contain a very specific compound called benzene. Now, benzene is in a ring shape, and its formula is C6H6, and it's a liquid at room temperature. Its general shape is a hexagon, so you actually have carbons in a hexagon shape like this, and they're all bonded to one another. And each one of these carbons is bonded to one hydrogen like this. Benzene is arguably the most important organic compound in organic synthesis or organic reactions. I can't stress that enough. And so it kind of has its own category. So anything that contains a benzene is considered aromatic. Anything that does not contain benzene is considered aliphatic, even the hydrocarbon derivatives. Now, what I want to focus in here is carbon needs to bond 4 times. That's what it prefers to do. And if you look at all of these carbons, they're only bonded 3 times. And so I'm going to add in here 3 double bonds like this. One on every second carbon, but this really isn't a true thing. There are no double bonds in benzene, but each carbon, if you put a double bond on every other carbon, is now bonded 4 times. So if I look again, here's 4 bonds around this carbon, and 4 bonds around that carbon, and 4 bonds around this carbon, and so on and so forth. What really happens, though, is these double bonds are actually 1 1/2 bonds all the way around. So there really isn't any double bonds. There's 1 1/2 bonds. This is an example of what we call resonance. The electrons are actually being shared perfectly even. So each carbon here on either side really has a 1 1/2 bond. And so if it has 2 1 1/2 bonds and then one other major bond, then that's a total of 4. So this is a structural diagram. We don't draw the structural diagram for benzene very often. A structural diagram shows every single atom and all of their bonds. This is generally how we show benzene. It's in a line diagram format, and it can be done in 3 ways. So it can be drawn like this with a double bond on every other carbon, or you can draw the same thing again, but the double bonds on the other spots like this. Again, I really want to enforce there are no carbon-carbon double bonds. There are not. The most modern way of doing it and how we do it now is generally a hexagon with a ring around the middle like this. All 3 of these represent benzene. All 3 of them are technically correct, and you can see any 3 of those on any type of question or problem. So again, keep in mind, benzene has essentially 6 carbons, 6 hydrogens. They are in a hexagon shape. Any one of these pictures I drew here are all 100% acceptable. Okay. Now, let's focus on the other side, which is aliphatic. So aliphatic means that you contain carbon and hydrogen, you're organic, but you don't contain a benzene ring. Now, aliphatics can be broken into 2 major subgroups. The subgroups would be saturated and unsaturated. These are both terms you absolutely must know. Now, saturated means the carbons themselves are bonded to completion, maxed out, no double or triple bonds there. So an alkane would only have carbon-carbon single bonds and be considered saturated. Now, unsaturated would have to have a carbon-carbon double bond, that would be an alkene, or a carbon-carbon triple bond, that would be an alkyne. Now, this does link to saturated and unsaturated fats, which we'll talk about in later episodes, but in this one, we're just kind of learning the basics. Now, what I want you to know about alkanes is that they have a generic formula of CnH2n plus 2 if they are in a chain format. Okay, so what I mean by a chain is they're not in a ring-like shape like benzene where they make a loop, whether it's a square or a pentagon or a triangle or a hexagon. It doesn't do that. And it will have no double or triple bonds. This formula is an alkane formula in that case. Alkanes, if they are a chain, are CnH2n, that's it, no plus 2. And this would have 1 double bond in the chain. And alkynes are CnH2n minus 2, and again, this is if it only has 1 triple bond. Technically, this formula could be 2 double bonds, but I don't want to confuse you quite yet, okay? Now, I'm sure there's probably a bit of confusion already with the fact that I have 2n plus 2, and what does this mean? So I'm going to give you an example. For all 3 of these scenarios, I'm going to start with the word prop. Okay, so I'm going to call this prop. I'm going to call this prop. I'm going to call this prop. Now, I'm sure everybody has heard of propane before. Propane bottles, they have, are used for fire tables or for barbecues, etc. There's 2 things going on in this name. The prop part of the name is telling me the number of carbons, which is 3. So in organic chemistry, prop means 3 carbons. So if I want to figure out the formula for propane, I go C3 because it's telling me prop. If it was meth, it would be C1. If it was eth, it would be C2. If it's prop, C3. We're going to learn all the names as we move forward. The ane part of it, which is part of alkane, is telling me how many hydrogens are on the compound and how I would calculate that. So for instance, ane is telling me this is H2n plus 2. So I go H, 2 times the number of carbons, 3, plus 2. Well, 2 times 3 is 6, and then plus 2 is 8, so this would be C3H8. So that's how I would figure out the chemical formula of propane, by looking at its name and understanding this formula. This is something that I would have to memorize and that I would ask you to memorize. So for instance, I could also have propene. So that's part of the alkene name, ENE. So again, prop means 3 carbons, so C3, but the ene means times 2. So this is H 2 times that 3. So its final answer would be C3H6. This is propene, and it would have 1 carbon-carbon double bond in it. Let's look at the last one, prop. So this is going to be C3, but now we're looking at ines. So an alkyne would be propyne. Now, the way I would figure that out is ines are telling me 2n minus 2. So this would be H2 times the number of carbons, which is 3, minus 2. So 2 times 3 is 6, minus 2 is 4. So this would be C3H4, and it would contain one carbon-carbon triple bond. Okay, we're going to change our focus and we're going to look at hydrocarbon derivatives. Now, I do want to point out before I get going that these are also aliphatic unless they contain a benzene ring as well. So although I didn't write aliphatic above it, they would still fall underneath aliphatic. Now, in our course, we're only looking at 4 different hydrocarbon derivatives. There are many more than this, okay? So we're going to be dealing with alkyl halides, alcohols, carboxylic acids, and esters. So again, I want you to remember it must contain carbon. It doesn't have to contain 2 other things, but they usually do. Usually they contain carbon, hydrogen, and then maybe something else like oxygen. However, they could contain only carbon and actually 1 other element. And where you will see that the most often is actually where we're going to start, which is alkyl halides. I could have something like CCl4 gas. So tetrachloromethane is what this would be called. It does contain carbon. It only contains 1 other element, and it contains no hydrogen in it as well. Other really famous ones for the alkyl halides would be things like CFCs, which destroy the ozone layer. And an example of that would be CF2Cl2. So chloral, fluoral, it has chlorine, it has fluorine, carbons, CFCs, chloral, fluoral, carbons. Quite often they do, however, have a hydrogen in them or 2, so something like CH2, Cl2 would also be an alkyl halide. You will find a lot of these in refrigeration, propellants, or even air conditioning units, things of that nature. Now, alcohols, and we're all comfortable or know the name alcohol, contains something called a hydroxyl group. Now, a hydroxyl group is a O bonded to an H like this. And you might look at it and say, hey, is that hydroxide? It's an O and an H. It is an O and an H, but it's not a hydroxide ion. It would be attached to some kind of group here I'm going to call R. And this R group here would have a carbon, might have lots of carbons and hydrogens. But this OH group here is the hydroxyl group. It's either written like that or even like this. And so probably 2 of the most famous alcohols would be methanol, CH3OH, or ethanol, C2H5OH. Ethanol being the alcohol that people drink. Methanol is used in lots of different things, methanol fuel cars, etc. You definitely cannot drink methanol. Our bodies convert that into formaldehyde, and it is known to cause people to go blind. A carboxylic group, or carboxyl group, form carboxylic acids. Now, carboxyl groups look like this, COOH, but if you actually expand it, it looks like this, C double bond O, single bond O, single bond H. So when you read a chemical formula and you think, why on earth are they writing it COOH? What they're trying to tell you is this COOH, the way it's organized, looks like this. And the reason why these are called carboxylic acids is it's this H here that ionizes in water to form a hydronium ion, and that's where the acid part comes from. Now, a couple of really famous carboxylic acids would be vinegar, the most common. It's called acetic acid or ethanoic acid. The reason it's called ethanoic acid is eth stands for 2 carbons, and if you look here, there's 2 carbons, and then the oic acid is telling me I have a carboxyl group. And so when we get to naming, we'll talk about this more, but essentially a carboxylic group would have an oic acid ending on the name. An alcohol will have an ol ending on the name. Now, another really famous carboxylic acid is a diprotic acid, oxalic acid, HOOCCOOH. It has 2 carboxylic groups, one on the left and one on the right, and it's diprotic because it has 2 different hydrogens that can ionize. Now, our last group is actually created by reacting an alcohol and a carboxylic acid together. It forms something called an ester. Now, the functional group for an ester is not called an ester group. It's actually called an ester link. It actually links the 2 main parts of a carboxylic acid and an alcohol together. It looks very similar to a carboxylic acid in that it is COO something else. This something else just cannot be hydrogen. It can be another carbon or something else. It just cannot be a hydrogen. And it looks similar. It's C double bond O, single bond O, something else. Okay, so there's our 4 hydrocarbon derivatives that we are going to learn about. We're going to learn how they react, their properties, how to name them, isomers, etc. But these are the only 4 that we have to look at our course. If you go online, you will see many, many other hydrocarbon derivatives. The next thing we're going to look at here is how is information shown in organic chemistry? Like, how can I draw a picture? What could it look like? What is the name of this style of picture? So the first thing I'm going to talk about is empirical formulas and molecular formulas. So a molecular formula shows you how many of each type of atom you have in a chemical compound. So for instance, this one has C4, H10, has 10 hydrogens, but it doesn't tell me how they are arranged. Now, an empirical formula, and sometimes people use them interchangeably, is the lowest ratio of carbons or to hydrogens or whatever it is you're dealing with. So an empirical formula for this would actually probably be C2H5. That's the lowest ratio. And for this one over here, it would be CH2O. Now, we generally do not deal with empirical formulas in terms of the lowest ratio. We really deal with molecular formulas, which tell us exactly how many atoms of each type of element we have. But sometimes chemists can use them interchangeably, or textbooks can, or YouTube videos can. And so I just want to make sure that we're clear. We're going to kind of call empirical formulas and molecular formulas the same thing, even though they're technically not. Okay, so this is the most simplistic way of showing what is in the organic compound. So over here on the right, this thing has 2 carbons, 4 hydrogens, and 2 oxygens, but it doesn't tell me how it's arranged. Now, the expanded empirical formula sheds more light on how these things are arranged. So for instance, when I look at this one, it's telling me I have a CH3 group, so grouped together of 1 carbon and 3 hydrogens. This is then attached to 2 separate CH2 groups, would go in a row, and followed by a CH3 group. So let me do some color coordinating for you here, and I'm going to turn this expanded empirical into a structural formula and show you how I did that. So for instance, I know I'm starting with a CH3 group, so I would go like this, CH3. There's my carbon and 3 hydrogens. This is then followed by 2 CH2 groups. So here's 1 CH2 group, here's 1 CH2 group, and then that's being followed by a CH3 group like this. So now I've taken something that was very generic, C4H10. I've turned it into something more descriptive. an expanded empirical formula. And now I've converted it into something called a structural formula, which shows all of the bonds and all of the atoms and how it's arranged. So now this is actually called butane. I know this because C4 is bute, 4 carbons is bute, and 10 is 4 times 2 plus 2, so this would be butane because of the way it looks. Okay, now an expanded empirical for this could be this. It looks like vinegar. The structural formula for that would look like this. So if I underline it, I would have CH3, and then that would be attached to a COOH group, which we learned was a carboxylic acid group, and we have to memorize that a COOH group looks like this. Now, something that happens in organic is we don't always put these lone pairs of electrons in. So don't be surprised if you don't see the lone pairs of electrons on the oxygens, and they may even just draw it as like this, COOH. There's nothing wrong with that as well. Now, a condensed structural basically lumps all the C groups, so CH3s and CH2s together, only showing a bond between the carbons. So for instance, if I was to bring my structural formula of butane down, I would have a CH3 group. This would be bonded to a CH2 group. This would be bonded to a CH2 group, so that would be this one, and then followed by a CH3 group, which would be this one. Now, although it looks like the hydrogen is making the bond with the carbon, it absolutely is not. There's just really no other way of showing it. Here, it can be shown a couple of ways. Most of the time you wouldn't show vinegar as a condensed structural, but sometimes you may. I've seen it written as this before, so CH3, COOH, but I've also seen it written as CH3 together, and the COOH being expanded out into the carboxylic group like that. Okay. Now, the last type of diagram, a line diagram, is one that you will come across a lot. It is a very popular one, especially for hydrocarbons, but it's used for all types of organic compounds. So what I'm going to do is I'm going to actually start with doing butane, and I'm going to draw the line diagram twice, and I'm going to overlay the second diagram with where everything is. So the line diagram for butane looks like this. Well, that seems a lot easier and a lot simpler, and that's why we do have line diagrams, is to speed things up. Now I'm going to draw it a second time because you're probably going, that makes no sense. So I'm going to draw it again, and I'm going to color coordinate this compound, butane, over top. So the beginning of every line and every vertex along the line, or every point along the line, represents a carbon. So for instance, this would be the blue carbon, here would be the red carbons, and here is my green carbon from my picture above. Okay, all right, then the thought is all of these carbons are bonded to their maximum capability, which is 4, to hydrogens, unless some other element has been introduced, which they haven't. There's no oxygens or anything there. So then I'm assuming that this carbon has 3 hydrogens on it because it's only got 1 bond, so it needs 3 hydrogens. This red carbon here is already bonded twice, so it only needs 2 hydrogens. Sorry. Same thing for the next one. It's bonded twice, so 2 hydrogens. And then this green carbon on the end, it's only bonded once, so it needs 3 hydrogens. And if you look at this diagram compared to our condensed structural up here, they look very similar, except you get this bendy up and down. Now, if you're wondering why is it bending up and down, if you remember back from bonding, you would know that when carbon bonds 4 times, it actually forms a tetrahedral shape, and it has bond angles of 109.5. And so this bending is trying to represent that kind of 109.5 bond angle, or even if it has a double bond, then it would have sp2 hybridization, and it would have 120 degree angle, but we draw it essentially the same. If you don't remember this, don't worry about it. Just understand that it kinks up and down. Every vertex represents a carbon unless something else is there, and that every carbon is bonded to its maximum capability. For this one here, this is what it would actually look like, and I'm going to draw it twice. So I'm going to start by showing you, I've kind of drawn one line longer than the other, okay, and this would be our blue carbon, that one there, and this one would be our red carbon. And now, because this is bonded to an O, the line generally is drawn a little bit shorter, and I have an O here. And sometimes it will be drawn with the OH like this, or sometimes it'll be drawn with the OH like this. But I'm gonna leave it together, OH like that, and then I would have double bond O like this. So that's the overlaid one. The actual one looks like this: double bond O, OH. This is the line diagram for vinegar. Again, I would have one carbon here, that's the blue one, CH3, and then I have this one here. This carbon again would be bonded 1, 2, 3 times to other hydrogens. That would be my CH3 group. Now, again, I'm going to give a little bit of a disclaimer. Different organic drawing programs online do variations of these diagrams. So for instance, if you went online, you might find a line diagram like this, but the computer program writes CH3 on the end like this instead of just leaving it as a line. It's very common. We don't really deal with that. And you can have some variations of condensed structural with line. So these aren't the only ways that you would see it if you did your own kind of studying online or in different textbooks, or using your own organic computer programs to draw different organic compounds. But for our course, these are really the ways that organic compounds are communicated to you on paper. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.